So this is a quick run through for differentiation from first principles. This is for A-level or AS math students studying in the UK and whatever the stupid Americans have, I've got no clue. The first half will just be me explaining the concept, then me running through some questions afterwards. So to begin with, what differentiation from first principles is just how the differentiation we use normally came about and the proof that goes along with it. And what differentiation means is just how we find the gradient function, or in other words, the gradient at any given point in a function. So what the equation states is that our differentiated equation, so the f dash of x, is the limit as h tends to 0 of f of x plus h minus f of x, all divided by h. Now this might seem complicated or confusing, but it is very simple, and this graph will help us show how we get there. So let's say the equation of the line said y is equal to 2x squared plus 3x or something like that. Now obviously this is not accurate, but let's just assume it said that. When we plug in some x value, so we're going to just plug in x. Even though I know it says x is over there, this x value could represent any number along the x-axis. So this is why we use it, and it's just by convention. It will spit out some y value, but we'll call this y value because it goes with x. We're going to say it's f of x. And here's the little trick. So we've got the point that goes for x and f of x. The little trick is that we actually add h to x. So we're going to have a point on our x-axis here where we have x plus h. So we go a little further along the x-axis by h. This will give you, as you can probably already tell, a different value for y. And just like our x, we're going to label this f of x plus h, as the x plus h gave us this value of y, which could be higher or lower, but it doesn't really matter as the gradient could be positive or negative. It just depends on the function we're differentiating. Now going back to our equation, we can see that it states that we have of f of x plus h minus f of x. Now on our graph, we can see that it's just this minus this, which will actually result in us finding the difference in our y between these 2 points. So where's this h come from where we divide by h? Where does it actually come from on the graph? As you might be able to guess and see, that it's actually the difference between our x values. So x plus h minus x, which will just result in us getting a difference of h. So what our equation and first principles is telling us is our difference in y's over our difference in x's, which is just actually our gradient. We're just finding out our gradient of these 2 points. So how does this make it any different from finding out what a differential is? Surely it's the same thing, right? It's actually where this limit of h tends to 0 actually comes into play. So to find the gradient of any given point, it is actually the tangent that comes off this point. So let's say x, for example, we're finding out the gradient between x. So our problem is that if we had 2 points that are quite far in distance apart from each other, if we join a line together and find out the gradient between them, now this is relatively close to the red line, but it's not quite what we're looking for. So that would have been, this part here would have been our x plus h, like our different x plus h. But let's say, and this overall distance here would have been our h difference. But when we limit our h to 0, what we're actually doing is bringing this point closer and closer and closer to x until we really actually are on the point x. Now the limit does not mean h is equal to 0, because otherwise we won't get an answer, because anything divided by 0 is undefined. There's no answer to that. But as it tends to 0, we're basically saying that we are making this h, this gap, so infinitesimally small that it practically might as well be 0, but it is not 0. I know that sounds a bit confusing, but this is the logic behind it. So we're finding a very, very small change in our height over a very, very small change in our distance across. So it'd look like that, and it would be like here. And this is what we actually end up getting is our dy by dx. The capital D is big delta for a big change. So when you have 2 points that are completely far apart, this is a capital delta. But the small d is obviously small delta, both Greek letters. So this is where differentiation actually comes from, and the proof behind it to be able to find the gradient at any given point in any function that you have. So that's the proof done. So onto the questions. You'll get very similar questions to this. They might vary, but the routine is always the same. The steps are always the same. So you have prove that 3x squared differentiated is 6x. And in the question, it will say prove by first principles. So don't worry about not knowing whether or not it will be there. It will always be there. My first step usually is to write out the equation. Even though it is given to you in the formula sheet, I usually write it out just so I've got it written down in front of me so I don't have to always look at the formula sheet to understand. And I like to label everything that I know and make it very clear to me what I'm subbing in. So we've got a function, our f of x will be our 3x squared. So what we haven't differentiated yet, but we're finding out what this differentiated goes to. And we know it's 6x, but we have to prove it. And this is where some students struggle a little bit. To find what our f of x plus h is, I'm going to previously explain why f of x is given to us as 3x squared. So what we're essentially doing is we have some kind of basically function. And all the function means is that we've kind of got like I want to say like it's a box, right? And what this box does is you got 3, and I'm going to write v for variable squared. So what this box does is if you give it an input, it will spit out an output. And this input will replace where v is. So in this case, we put, as our function, we put x to start off with. So it will spit out 3x squared. And if we apply the same thing again, so if I duplicate this and say, instead of saying x, we're going to put in brackets, x plus h. Since that's how far we've moved along the x-axis, like I've shown above. We're going to replace where our v is and say we've got actually 3x plus h all squared. And that is what our f of x plus h will be equal to. Some students struggle with this idea, but take it slow and just try to understand where this is coming from. I feel like knowing the proof prior kind of helps you visualize and understand why we get this x plus h and where it comes from. So continuing forward, I'm just going to delete all this stuff prior. So moving forward, we've got everything labeled up. So our next line, we're going to have to write limits. So lim, h tends to 0. And you will have to write that for every single line to get all the marks. Because I guess the examiner will look at it and think like, oh, so what happens in this line? Maybe there was no limit to h. What, it only exists on some lines don't. Mathematically, it has to exist. It has to be on every line. And even though we kind of get what you're saying, it just needs to be there to get the marks. So I know it's annoying, but just have to do it. So we have limit h to 0 of, we plug in our f of x plus h, which is 3x plus h all squared, minus 3x squared, which is our f of x, all over h. So we expand this, since that's the only thing it looks like we can do. We're going to have 3 lots of x squared plus 2xh plus h squared minus 3x squared, all on h again. And again, we write another line expanding this. So lim h tends to 0 of 3x squared plus 6x h plus 3h squared minus 3x squared, all on h. So now we can see our 3x squareds are able to cancel, since we got 3x squared minus 3x squared. And now we have everything that is divisible by h. We can divide by h here. So we're going to say lim h tends to 0 and divide by h. So 6xh divided by h will just give us 6x. And 3h squared divided by h will give us plus 3h. And at this point, now we can limit our h to 0. So we basically plug in wherever we see a h, 0. So we have 6x plus 3 lots of 0, which is obviously just disappears. So we finally get 6x as a final answer, and that's what f dash of x is equal to. And that will get you every single mark in an exam for this type of question. So on to question 2. Point A has coordinates -2, -8, and lies on the curve y equals x cubed. At point A, the tangent has a gradient g. And part A asks us to show that g is equal to the limit of h tends to 0 of 12 minus 6h plus h squared. So again, as I started the last question, write out our first principles equation. And from the get-go, from the start of this question, the whole way you can kind of realize that it's asking for first principles is this limit h tends to 0. You won't see that anywhere else in the A level, and you won't see it in the AS. This only is for first principles, so that kind of gives you a hint to start off with. So again, I'm going to do everything that I did before. I'm going to find out what my undifferentiated function is, that we're trying to find out what is differentiated, or what is differentiated, which is x cubed, and what our f of x plus h would be. So we're going to write f of x plus h. Again, we're putting it into the function box, which means we're replacing where x is with x plus h. We're going to get x plus h cubed. And we're showing that g is equal to this 12 minus 6h plus h squared. So we've got everything we need right now, so we just sub everything in. We've got x plus h cubed minus x cubed over h, and that's all being limited when h tends to 0. So then we expand this out, and I mean, you can use Pascal's triangle if you have learnt that yet. So we know that the limit of h tends to 0, you will get x squared, so the binomial expansion as well, x cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed, all on h. So again, we write another line where we say limit h tends to 0, and we can see our x cubes cancel, since x cubed minus x cubed cancel, and everything else again is divisible by h. So at this step, we do every single one and we'll divide it by h. So 3x squared h divided by h will just give us 3x squared. 3x h squared divided by h will give us 3xh. And then just h squared, or h cubed divided by h will give us h squared. And I believe this is almost what they're asking for. But they're asking for it at the point A. So we know that at this point, we actually have to sub in, because this is what our gradient is, the -2 and -8. However, the -8 is for our y, and all we have is x's here. So what we will do is just sub in our -2, and this should fix all our problems. So we got 3 lots of -2 squared plus 3 lots of -2 plus h squared. And if we limit h tends to 0 of this, so -2 squared is 4. 4 times 3 is 12. So we have 12, and then 3 times -2 is -6h plus h squared. And that is exactly what they asked for. So part A, and we're going to call this G since it's the gradient at A, is proven like that. Then we go into part B where it says deduce the value of G. And what this is just saying finish off basically what you started. Find out what G is. So we've still got our G is equal to the limit of h tends to 0, 12 minus 6h plus h squared. There's no further simplifying we can do to this, maybe factoring out h's or whatnot, but now all we really can do is limit our h to 0. So we basically substitute everything in that is a h as 0, which will give us 12 minus 0 plus 0, which is just going to be 12. So our G is actually just 12. And it wasn't that bad. But that is the type of question and type of part B you would receive in an exam. The final question I've got written out. This one is also a potential that could come up in an exam. I've had this before in a past paper. To do this, again, same principles as I've shown, that this is a variable and it can be replaced always. So it doesn't have to say f of x there, so you shouldn't be thrown off by it. It's just the same steps but with different variables, which is completely fine to do. So again, we're going to write out, and this time I'll write it out. We've got f dash of x is equal to the limit of h tends to 0 of f of x plus h minus f of x all on h. And I've remembered it because I've done so many times, and you'll pick it up very quickly as well. And do enough questions like this and you'll be completely fine if it ever comes up. So our undifferentiated equation is as it states there at the top. F of z is equal to az squared. Now, what we can do, if it makes it easier for you, is we can actually replace all the x's before you even wrote them with z's, so that the same thing applies. Because the same way that this is a variable here for the z, the x's prior were the same thing. It's just a variable. It doesn't matter what they actually are. They can all be replaced with different things or different variables. So finding out f z plus h is just replacing our z with z plus h. So we're going to have a lots of z plus h all squared. So again, we've got everything we need, so we just follow the steps again. So limit our h as it tends to 0 of f of z plus h, which is a z plus h squared, minus a z squared, which is our f of z, over h. So we followed the same steps again. So limit h tends to 0, expand. We're going to have a lots of z squared plus 2zh plus h squared minus a z squared, all on h. Expand this so that you get the limit of h tends to 0 of a z squared plus 2azh plus a h squared minus a z squared, all over h. So again, our a z squareds cancel. You'll see this often, that if the top of your fraction is not divisible by h, not every single thing is divisible by h, you have done something wrong with your expansion, something along those lines, your subtraction. But everything at the top has to be divisible by h. And if you haven't got that, then there's something that went wrong in the workings out. That's a hint for you to know whether or not you've went wrong. So we continue and we divide everything by h. So we'll end up with 2az plus ah. And there's nothing else for us to really do. Maybe we can factor out the a's, but it's really subbing in where 0, h for 0. So instead of writing lim, I'm so used to writing it, you just get rid of the ah, since a times 0 is just going to be 0. So you get 2az as the final answer. And that is exactly what is asked for you to write and find. So f dash of z is equal to 2az. And that's the final example done.